In a previous video, we covered Euclid's proof of the irrationality of the square root of 2. But in mathematics, the same truth can be proven in different ways. Today, we'll look at another proof. At first, it seems like it should be quicker, but in the end, it turns out to be longer. And in the process, we'll see why Euclid's original method is still considered the most elegant. Let's quickly recap Euclid's proof. He assumes that the square root of 2 could be written as a fraction of integers a by b, where the HCF of a and b is 1. This led to the equation a squared equals 2 times b squared. From this, he showed that a must be even. He then assumes that a equals 2k, where k is an integer, since a is even. Substituting 2k in place of a, he showed that b would also be even, contradicting the fact that a and b were supposed to have no common factor. And just like that, we're done. Simple and sharp. Now let's try the alternative proof. Again, we assume that the square root of 2 equals a over b. Squaring both sides gives a squared equals 2 times b squared. That means the square of an integer, a squared, is exactly double another square, b squared. Now here comes the idea. Is it possible for 2 times a perfect square to itself be a perfect square? Let's look at some examples. Double of 1 squared is 2. Not a perfect square. Double of 2 squared is 8. Still not a square. Double of 3 squared is 18. Double of 4 squared is 32. None of them are squares. It looks like doubling a perfect square never gives a square. That would mean a squared can't equal 2 times b squared, which proves square root 2 is irrational. But hold on, just checking examples is not a proof. We need to show this works for every square, not just a few small ones. And this is where the Fundamental Theorem of Arithmetic comes in. The Fundamental Theorem of Arithmetic states that every integer greater than 1 can be uniquely expressed as a product of prime numbers, disregarding the order of the factors. That means any perfect square must have all its prime factors paired up. For example, 36 equals 2 times 2 times 3 times 3. Every prime factor appears an even number of times. But now look at 2b squared. Since b squared is a square, all the primes in b squared are paired. But then we multiply by 2. That leaves one extra factor of 2. Which means 2b squared can never be a perfect square. This is the rigorous reason why a squared equals 2b squared is impossible when a and b are integers. And that completes the alternative proof. So now we can compare. Euclid's proof is short, direct, and works just with the idea of even and odd numbers. The alternative proof also works, but it requires a heavier tool, the Fundamental Theorem of Arithmetic, and ends up longer. In mathematics, the same fact can often be proven in many different ways. But the most elegant proof is usually the shortest one that says the most with the least. And that's why Euclid's version is considered the classic. Thanks for watching, and don't forget to like, share, and subscribe for more Class 10 real numbers lessons.